Hello again. We're going to do a sample problem now involving rate data. So how do we determine the rate law, the order with respect to various reactants if we have this type of data? I talked about this in the slides, but of course it's going to make way more sense if you actually see it. So if we have this reaction right here, and we monitor, we essentially set up multiple reaction vessels. So what we're doing is starting with differing concentrations of those reactants and monitoring how they affect the rate or the initial rate. So we have 4 reaction vessels. With 4 different setups for differing concentrations of those 2 reactants, and we're able to monitor that initial rate and see how does changing the concentration of these reactants affect that rate. So what we have to do is, like I said, we have 2 variables, we have 2 reactants. So we have to find one of these vessels, or two of these vessels where we're changing the concentration of one of the reactants, but not the other. So let's say we wanted to do CH3Cl, the chloromethane, 1-chloromethane. We could probably take vessels 1 and 2. You can see that we're doubling the concentration of the CH3Cl, but holding the concentration of the Cl2 minus. And what this is going to look like then is the rate is going to be equal to that change in concentration raised to whatever, we'll say M, whatever the order of that reaction is. So let's look at our 2 rates and compare them. We have this is our second rate, and that is our first rate. And for our concentrations, we have this over that raised to the M. So what do we have here? Essentially 2. I think it's slightly more than that, just due to probably variation in the data. So you have 2.07 equals 2 raised to the M. If you're relatively close to that actual value, I would count this as 2. Like I said, this is experimental data, so depending on the precision of the device, you might be off a little bit. I would say that's a 2. So you have 2 equals 2 raised to the M. What's M going to be? It's going to have to be first order, 1. 2 raised to the 1 equals 2. So that one's relatively straightforward in regards to what the reaction order is. We're going to go to the next one now and see that sometimes we're not going to have as nice, as straightforward of a problem as that. Let's start here. Let's make sure we denote that reaction order for now. And let's do the same thing with the Cl2. Let's take reaction vessel 2 and 3 now. So here the concentration of CH3Cl is held constant, but the Cl2 changes and our rate changes. So we're going to have our rate differences accounting for how much did we, what factor did we change that rate by, and then our concentration changes over here raised to, we'll call this one N. So what I get, I believe, is 1.41. Yep. So I've got 1.41 equals 2 raised to the N. Now, some of you might know in your heads, be able to see that, what that is. If not, what we're going to do to solve for N is we take the log of both sides. So I have log of 1.41 equals, and then the N is, sorry, the N is going to come out in front. So this is going to be N times the log of 2. If I do that, what I should get is, yep, we'll move over here for a second. 0.1149 equals N log of, not log, we're going to work the calculation already. 2 is 0.30. So now if I want N, I'm going to divide this side by that. So in this case, n is or equal to 1/2 or the square root. So our reaction order for the Cl2 would be 1/2. And that's possible. We will find that you don't always have things that go by a nice, easy reaction order that's always 0, 1, or 2. You could see a 1/2 or 3/2 where it's not as dependent or not quite as linearly dependent or exponentially dependent on that particular reactant as it may be others. So we have our reaction order, and then if we can actually find our K as well, simply by grabbing any one of these lines and filling everything in. So remember, rate is equal to the rate constant times all this raised to the appropriate order. And of course, if it's first order, a lot of times we'll just leave that one out, but we'll put it there now just to keep track of it. So what I could do now is substitute all these values in. If we take line 1, I know the rate, I know the concentration of this, and I know the concentration of that, and I can plug all those values in. Yep. And we have our K being equal to 1.25. And we want to track the units here. This should be molarities to the 3/2 over seconds, I believe. But we'd have our entire expression now, our rate constant and the specific order for each reactant or component involved in the reaction, just from this table. So hopefully that was helpful, seeing that in practice. Definitely work some problems like that, try to replicate it. I'm going to stop here so the video isn't too long and unwieldy, and I'm going to solve a couple different types of problems in the next video.